Imagine a spaceship so large that clouds form inside it. Rain falls on its farmland. Rivers run through its corridors. 10 million tons of steel, rock and atmosphere spinning through the void, carrying a population the size of a small city. This is not science fiction. NASA studied how to build it in 1975, and the engineering has only grown more terrifying since. Because the hardest part is not making something big. The hardest part is that every system keeping you alive on Earth, gravity, air, radiation shielding, heat rejection, food, water, waste must be rebuilt from raw physics inside engineered walls. And if a single one of those systems fails for longer than a few days, everyone inside dies. This is how you would actually have to build it. If you enjoy journeys that make engineering feel as vast as the cosmos itself, go ahead and hit that like button and subscribe. It genuinely helps this channel keep making deep explorations like this one. Now, settle in. Get yourself comfortable. Let's begin. Close your eyes and picture a spaceship bigger than a city. Whatever you just imagined is wrong. You probably pictured something sleek, a massive hull cutting through darkness, glowing engines at the back, maybe a bridge at the front where a captain stares into the void. That image comes from decades of science fiction, and it has almost nothing to do with what this object would actually need to be. The sleek ship works in movies, because movies do not have to obey thermodynamics. They do not have to feed a population, or stop galactic cosmic rays, or reject waste heat into a vacuum. Reality does, and reality does not care about aesthetics. A city-sized spaceship is not a vehicle, it is a world. And the difference between building a vehicle and building a world is the difference between driving across a continent and carrying the continent with you while you walk. Every spacecraft humanity has ever built is a vehicle. The Apollo capsule was a vehicle. It carried enough oxygen, water and food for 3 people for roughly 2 weeks, and it relied on Earth for everything before and after. The space shuttle was a vehicle. It returned to the ground after every mission to be refueled, repaired and restocked. The International Space Station, despite being the most complex structure ever assembled in orbit, is fundamentally still a vehicle. It carries supplies, it stores oxygen in tanks and water in containers. It depends on cargo missions from the surface for food, spare parts, replacement hardware, and even the occasional emergency repair tool. When a pump breaks on the station, a replacement rides up on the next cargo flight. When the water recycling system falters, ground controllers in Houston walk the crew through repairs using components shipped from Earth. The station is extraordinary, but it cannot survive without its home planet. It was never designed to. Now imagine severing that lifeline completely. Imagine a structure so far from Earth that no cargo mission can realistically reach it. No replacement parts are coming. No emergency evacuation is possible. Every breath of air, every sip of water, every calorie of food, every watt of electricity, every replacement gasket and filter and bearing must come from systems that exist inside the walls. And those systems must work not for months, not for a few years, but for decades, possibly centuries. That is what a city-sized spaceship actually requires, not a bigger version of what we have already built. Something fundamentally, structurally, and operationally different. Something that has never existed in human history. The first real attempt to design this object happened in 1975, and the results were terrifying. NASA and Stanford University conducted a joint summer study that year, bringing together dozens of engineers, physicists, architects, and agricultural scientists to answer a seemingly straightforward question. How would you design a permanent space habitat for 10,000 people? Not a space station, not a temporary outpost. A permanent settlement where people would be born, grow up, work, grow old, and die without ever needing to return to Earth. The result was the Stanford Torus, published as a NASA design study. It proposed a ring-shaped rotating structure, approximately 1.8 kilometers in diameter, a hollow donut about as wide as a large town, spinning once per minute to generate Earth-normal artificial gravity on the inside of the outer ring. Sunlight would enter through a system of angled mirrors. The interior would contain residential neighborhoods, parks and recreation areas, small rivers and ponds, and dedicated agricultural zones. 10,000 human beings living, working, and raising families inside a manufactured world orbiting at the Earth-Moon L5 Lagrange point, a gravitationally stable region in cislunar space. The design was elegant. The physics was sound. The architectural renderings showed rolling green hills under a simulated blue sky, pedestrian pathways curving gently upward in the distance as the floor of the ring arced overhead, and small communities nestled among trees and gardens that would have looked perfectly natural in coastal California. The study was meticulous. It calculated how many hectares of cropland were needed to feed the population. It specified the mix of grains, vegetables, legumes, and fruits required to sustain a balanced diet. It accounted for livestock areas, aquaculture tanks, food processing facilities, and agricultural waste composting. It designed the residential districts, the recreation areas, the light industrial workshops, and the zero-gravity hub at the center of the ring where spacecraft would dock and cargo would be transferred. The Stanford Torus was not a sketch on a napkin. It was a serious, funded, peer-reviewed engineering study conducted by some of the best technical minds of its era. And then those same engineers calculated the mass. 10 million metric tons. That is how much the completed Stanford Torus would weigh when fully assembled, filled with atmosphere, loaded with soil and water, and wrapped in radiation shielding. 10 million metric tons of steel, aluminum, glass, processed lunar regolith, breathable atmosphere, water, agricultural soil, and biological material. To grasp that number, consider that the International Space Station, the single largest structure humanity has ever placed in orbit, the product of 16 nations collaborating over more than a decade, has a mass of roughly 420 metric tons. The Stanford Torus would be approximately 24,000 times more massive. Picture 24,000 International Space Stations worth of material, somehow transported to a point in deep cislunar space and assembled into a single spinning ring. That is the Stanford Torus. That is the small design. But the mass figure conceals something even more disturbing. 95% of those 10 million tons is not habitat. It is not living space, or farmland, or corridors, or machinery. 95% of the total mass, roughly 9.5 million tons, is radiation shielding. The walls of processed rock and regolith that keep cosmic rays and solar particle events from slowly killing everyone inside. Strip away the shielding and the actual habitat, the portion where human beings live and breathe, weighs only about 500,000 tons. The livable structure is buried inside a mountain of armor. You are not building a home in space. You are building a fortress. And the fortress is almost entirely made of walls. 1 year after the Stanford study wrapped up, Princeton physicist Gerard K. O'Neill published his book The High Frontier, proposing something far more ambitious. The O'Neill cylinder consists of 2 counter-rotating cylinders, each approximately 8 kilometers in diameter and 32 kilometers long. To put that in perspective, each cylinder is wide enough to fit the entire island of Manhattan across its interior floor with room to spare, and long enough that you could lay 1.5 Manhattans end to end along its length with kilometers left over. Each cylinder is divided into 6 strips running its full length 3 land panels, alternating with 3 enormous window panels. An outer agricultural ring, roughly 32 kilometers in diameter, rotates at a different speed to support dedicated farming operations. The total habitable land area inside a pair of O'Neill cylinders is approximately 500 square miles. Several million people could live inside this structure, complete with weather, terrain variation, and an artificial sky that curves upward on both sides until it meets overhead. The mass of a steel O'Neill cylinder is almost beyond language. One engineering analysis calculated that building a steel O'Neill cylinder and launching the material from Earth would require roughly 50 million heavy-lift rocket launches just for the structural shell, with another 27 million launches for the atmosphere and interior contents. 77 million rocket launches. Using the most powerful rocket currently in development, capable of carrying approximately 100 tons of payload to low Earth orbit per flight. 77 million flights of a vehicle that currently launches a few times per year. This is not a logistics challenge. This is a physical absurdity. To launch 77 million payloads of 100 tons each, you would need to burn more rocket propellant than currently exists in refined form anywhere on Earth. If you launched 1 rocket every single hour without pause, 24 hours a day, 365 days a year. The campaign would take nearly 9,000 years. Speed it up to one launch every 10 minutes, a pace that would require dozens of launch sites operating simultaneously around the clock, and it still takes over 1,400 years. The exhaust emissions from that many chemical rocket launches would measurably alter the composition of Earth's atmosphere. The manufacturing pipeline for 77 million rocket stages and engine sets would consume a significant fraction of global industrial output for generations. And at the end of this impossible effort, you would merely have placed raw material in low Earth orbit, not at the construction site. You would still need to transport every single ton from low orbit to the L5 point, hundreds of thousands of kilometers away, at additional energy cost that roughly doubles the total propellant requirement. This is why every serious habitat study conducted since the 1970s has reached the same foundational conclusion. You cannot build a city-sized spaceship by launching material from the surface of a planet. The gravity well is too deep, the energy cost is too high, the mass is too great. If this object is ever constructed, it must be built from materials already in space. The structure must be born in the void, not carried into it. But before we get to where the materials would come from, we need to understand why the structure demands such staggering mass in the first place. And that means confronting a force that most people have never heard of, but that dominates every aspect of rotating habitat design. It is the force that determines how large a habitat can be, what materials it can be made from, and how close to destruction it lives every second of its existence. It is called hoop stress, and it is the reason a spinning space habitat tries to tear itself apart. Every rotating habitat generates artificial gravity through centripetal acceleration. Spin the structure, and the floor pushes against your feet the same way a car door presses against your shoulder when the car takes a sharp turn. Stand on the inner surface of the outer wall of a spinning cylinder, and you feel weight. The larger the radius and the faster the rotation, the stronger the apparent gravity. To simulate Earth normal gravity approximately 9.8 meters per second squared, the habitat must spin at a rate determined by its radius. A structure with a radius of 250 meters needs roughly 2 revolutions per minute. A structure with a radius of 4,000 meters needs only about half a revolution per minute. Bigger is gentler. Bigger is more comfortable. Bigger feels more like standing on solid ground. This sounds elegant, and it is right up until you calculate the forces tearing the structure apart. When the habitat spins, every kilogram of material in the shell, every ton of radiation shielding piled on the interior surface, every cubic meter of pressurized atmosphere pushing outward, all of it is being flung toward the outside by the rotation. The outer shell of the habitat must resist this outward force through tension, the same way a spinning bicycle wheel holds together through the tension in its rim. The technical term for this tensile stress in a spinning ring or cylinder is hoop stress. And hoop stress increases with 2 factors simultaneously: the density of the shell material and the radius of the habitat. The governing relationship is deceptively simple. Hoop stress equals density times gravitational acceleration times radius, but the consequences are savage. Double the radius, and you double the stress trying to rip the shell open. Use a denser structural material, and the stress climbs proportionally. And here is the truly brutal part, the part that keeps habitat engineers awake at night. The radiation shielding and structural material that you desperately need to protect the habitat and hold it together also adds to the centripetal load that the structure must support. The armor is fighting against itself. The heavier your walls, the stronger they must be to keep from flying apart, which requires thicker walls, which makes them heavier, which means they need to be stronger still. It is a vicious upward spiral of mass chasing strength, chasing mass. This creates a hard ceiling on how large a rotating habitat can be for any given construction material. For structural steel, the maximum practical radius for a habitat spinning at 1 g sits somewhere in the range of a few thousand meters before the required wall thickness becomes absurd. The O'Neill cylinder, at roughly 4,000 meters radius, sits dangerously close to the theoretical limit for steel construction. Push much beyond that radius, and no achievable thickness of steel can hold the structure together. The habitat shreds itself under its own spinning weight. Advanced materials push the limit outward. Carbon fiber composites offer a much better strength-to-density ratio than steel, permitting larger radii before structural failure. Carbon nanotubes, if they could ever be manufactured in bulk structural form, would theoretically allow habitats hundreds of kilometers across. The McKendree cylinder concept, proposed in the late 1990s, imagined nanotube-based cylinders 460 kilometers in radius. But carbon nanotubes do not currently exist as a structural building material at any meaningful scale. No one has produced a sheet of structural-grade nanotube composite large enough to cover a desk, let alone wrap around a habitat 8 kilometers wide. Building a city in space from a material that does not yet exist introduces a different category of engineering problem, one that no equation can resolve. A recent proposal could change the math at a fundamental level. Researchers presented work in 2024 on structural decoupling, separating the rotating habitat ring from the load-bearing structural shell using superconducting magnetic levitation. In this design, the inner ring rotates freely inside a static outer ring that does not spin. Because the outer structural ring stays motionless, it never experiences centripetal force from its own mass. The self-reinforcing weight problem vanishes. Theoretically, this allows habitats of arbitrary size built from ordinary materials. The concept has been demonstrated in laboratory-scale models, but it remains far from engineering validation at anything approaching real habitat dimensions. It is a promising physical principle. It is not yet a construction plan. For now, any habitat built with current or near-future materials faces hard structural limits, and those limits force deeply uncomfortable design trade-offs. Consider the relationship between radius, rotation rate, and human comfort. Spin a habitat with a very small radius, and the rotation rate must be high to generate 1 g of apparent gravity. High rotation rates create powerful Coriolis effects, the apparent sideways deflection of moving objects inside the spinning reference frame. Inside a rapidly spinning habitat, physics feels wrong in ways that are viscerally disturbing. Drop a ball and it does not fall straight down. It curves visibly to one side, tracing a path that looks like an invisible hand is pushing it. Walk in the direction of the spin and you feel noticeably heavier, your legs working harder with every step. Turn around and walk against the spin and you suddenly feel lighter, almost buoyant. Throw a ball to a friend standing 10 meters away and it swerves off course, missing them entirely. Pour water from a pitcher and it arcs sideways on the way down, splashing onto the table beside the glass rather than into it. Climb a ladder and feel your weight shift laterally as your altitude changes relative to the spin axis. These effects cause persistent nausea, spatial disorientation, and debilitating motion sickness that does not go away because the environment is always spinning. Research suggests that most people cannot tolerate rotation rates above approximately 2 revolutions per minute without significant discomfort. Some studies place the practical comfort threshold lower, at 1 to 1.5 revolutions per minute, though individual tolerance varies. This comfort constraint sets a minimum radius. If you want Earth normal gravity at no more than 2 revolutions per minute, the radius must be at least 224 meters. If you want to keep the spin rate below 1 revolution per minute, the threshold, NASA's 1975 study used, the radius must be at least approximately 900 meters. The Stanford Torus was designed at roughly 900 meters for precisely this reason. The O'Neill cylinder, at 4,000 meters, rotates so slowly that Coriolis effects at floor level are negligible. You could play catch inside an O'Neill cylinder without noticing anything unusual, but that comfort costs you 4,000 meters of radius, and 4,000 meters of radius costs you structural mass on a scale that buries every other engineering concern. The Kalpana 1 design, developed at NASA Ames Research Center and revised in 2007, pushed the optimization further. Named for astronaut Kalpana Chawla, it uses a short, stubby cylinder, 250 meters in radius and 325 meters in length proportioned, so the structure is wider than it is tall, ensuring passive rotational stability. Long, skinny cylinders spinning in zero gravity are unstable. Give them a nudge, and they eventually tumble end over end, which would be instantly fatal for the residents. Kalpana 1 avoids this by keeping the length-to-radius ratio below the stability threshold. The trade is a smaller population. Kalpana 1 supports roughly 3,000 people, housed in a structure with a total estimated mass of approximately 7 million tons. 7 million tons for 3,000 people. Divide that figure out. It comes to roughly 2,300 tons of structure per person, most of it radiation shielding. Every man, woman, and child living inside this habitat is surrounded by more than 2,000 tons of processed material whose primary function is to stop high-energy particles from shredding their DNA. On Earth, the atmosphere provides shielding equivalent to roughly 10 meters of water stacked above your head. The planet's magnetic field deflects the vast majority of charged particles before they even reach the upper atmosphere. We live at the bottom of an ocean of air, wrapped inside a magnetic force field generated by convection currents of molten iron churning deep beneath the surface. We never think about this protection because we never have to. It is invisible, constant, and free. In space, all of that vanishes. There is no atmosphere. There is no planetary magnetic field. There is only vacuum and radiation and silence. And the radiation never stops. But shielding mass is only one component of the total. Consider the atmosphere itself. A city-sized habitat must contain a breathable atmosphere at something close to standard sea level pressure, roughly 101 kilopascals. That atmosphere has mass. Air at sea level density weighs approximately 1.2 kilograms per cubic meter. The interior volume of a Stanford Torus is roughly 61 million cubic meters. Fill that volume with breathable air, and the atmosphere alone weighs over 73,000 tons. That is more than 170 international space stations worth of mass, just in gas. Gas that must be manufactured or extracted from raw materials, purified, transported to the construction site, sealed inside walls strong enough to contain it against the vacuum outside, and maintained at the correct composition indefinitely. Too much carbon dioxide, and people suffocate. Too much oxygen and a single spark becomes a catastrophe. The atmosphere is not passive. It is an actively managed system that must be monitored and corrected continuously. And the air pushes outward against the shell. Just like the shielding and the structure itself, the pressurized atmosphere exerts force on the walls. This internal pressure adds to the hoop stress. At 1 atmosphere of pressure inside a cylinder with a 900-meter radius and a shell 20 meters thick, the circumferential stress from air pressure alone reaches significant values tens of megapascals. At large radii, this is not the dominant stress. The centripetal load from the spinning shielding mass usually exceeds it, but it is not negligible. You cannot have humans without air, you cannot have air without pressure, and you cannot have pressure without additional stress on the walls. Every component adds load. Nothing is free. Now add water. Each person requires water for drinking, hygiene, food preparation, agriculture, and industrial processes. The total water mass circulating through the life support system of a 10,000-person habitat, distributed across reservoirs, soil moisture, plumbing, recycling systems, and agricultural irrigation amounts to thousands of tons at minimum. All of it pressing outward against the spinning floor, all of it adding to the centripetal load. Add soil. The Stanford Torus study allocated approximately 63 hectares of agricultural land to feed 10,000 residents. That soil has depth, density, and weight. Even a modest growing medium of 30 centimeters depth spread across 63 hectares creates nearly 200,000 cubic meters of substrate, weighing hundreds of thousands of tons depending on composition. All of it sitting on the inside surface of the spinning ring, pressing outward, adding to the structural burden. Add machinery, power generation systems, water treatment and recycling plants, air revitalization units, lighting arrays, communication networks, transportation infrastructure, medical equipment, manufacturing workshops, warehouses and storage bays, docking ports and airlocks, repair facilities, emergency shelters. Each system has mass. Each system occupies volume. Each system presses against the floor of a spinning world that must hold together against forces no terrestrial building has ever experienced. The total picture is staggering. A city-sized spaceship is not a hollow shell with some people floating inside. It is millions upon millions of tons of material distributed across dozens of interdependent categories: primary structure, radiation shielding, pressurized atmosphere, water reserves, agricultural soil, biological material, mechanical infrastructure, electrical systems, thermal management hardware, all spinning together, all pressing outward, all straining against walls whose integrity determines whether 10,000 people continue breathing or die in seconds. And nothing even remotely this massive can be launched from the surface of a planet, not from Earth with its crushing gravity, not from Mars, not from anywhere with a meaningful gravity well. The mass is simply too vast. The energy required to lift 10 million tons into Earth orbit exceeds anything human industrial civilization has ever generated for a single purpose. Estimates suggest the cost would dwarf the entire global economy for years, running, possibly decades. So the material must come from somewhere with weaker gravity, somewhere already above the steep walls of a planetary gravity well. The Moon, at 1/6 of Earth's surface gravity, is the most commonly proposed source. Gerard O'Neill envisioned electromagnetic mass drivers, essentially linear accelerators built on the lunar surface, flinging canisters of processed regolith into space at precisely calculated velocities to reach the L5 construction site, where robotic mass catchers would collect the material for refining and fabrication. The physics works. The engineering is plausible. The required infrastructure does not yet exist in any form. Near-Earth asteroids offer another path. Some contain water ice, carbon compounds, nickel, iron, and silicates, useful raw materials for construction. A single metallic asteroid a few hundred meters across may contain more accessible iron and nickel than humanity has mined throughout all of recorded history. Extracting and processing that material in microgravity, using concentrated solar energy, eliminates the gravity well problem entirely. But asteroid mining in 2026 remains in its earliest experimental phase. The first commercial deep space prospecting missions have only just begun, and none has yet completed a successful asteroid rendezvous. The gap between sending a small probe past a distant rock and operating an industrial-scale extraction facility capable of producing millions of tons of processed metal and regolith is measured in decades of development, not years. This is the first great revelation of habitat engineering, and it is the one that changes everything about how you think about the project. The city-sized spaceship cannot exist in isolation. It requires an entire industrial civilization already operating in space before a single wall panel can be fabricated. You do not build the habitat and then develop space industry to service it. You develop space mining, orbital refining, zero-gravity smelting, automated manufacturing, and robotic assembly first. And the habitat is the product of that industrial ecosystem. The spaceship is not the beginning of the story. It is the culmination of a story that has not yet started in earnest. And yet, even if every material challenge were solved tomorrow, if lunar mass drivers were operational, if asteroid mining were routine, if orbital factories could produce structural steel and process regolith shielding at industrial scale, you would still face the three physical constraints that truly determine whether the habitat lives or dies. Gravity must be manufactured through rotation, with all the structural punishment that entails. Radiation must be stopped with raw mass, measured in millions of tons. And heat, the silent, invisible killer that almost nobody outside of aerospace engineering ever considers, must be radiated away into the emptiness of space through enormous exposed surfaces that cannot be armored, cannot be hidden, and absolutely cannot be allowed to fail. What comes next is how each of those three constraints actually works, why each one is far harder than it first appears, and why solving all three at once, inside the same spinning structure, is the central engineering nightmare of building an artificial world. You now know the scale. You know the mass. You know that this structure cannot be launched from Earth and that its own spinning weight threatens to destroy it. But understanding the numbers is only the first layer. Beneath the numbers lie three physical systems that the habitat must solve simultaneously or kill everyone inside. These are not optional features. They are not amenities. They are the physics of survival. Artificial gravity through rotation, radiation shielding through brute mass, and thermal control through exposed radiators that cannot hide behind armor. Each one of these systems is an engineering nightmare on its own. Together, they form a set of constraints so tightly interlocked that solving one often makes another worse. Start with gravity, because it affects everything else. We have already seen why the habitat must spin to generate weight, and why that spin introduces Coriolis forces and structural stress. But there is a deeper strangeness to living inside a rotating cylinder that most discussions of artificial gravity never mention. Gravity inside a spinning habitat is not uniform. It is not constant across the interior the way gravity is essentially constant across a room on Earth. Inside a rotating structure, gravity changes with altitude, and it changes fast. On Earth, if you climb 10 meters up a staircase, gravity barely shifts. The difference is roughly 3 parts per million. You could carry the most sensitive accelerometer ever built up a 10-story building, and the reading would not visibly change. This near uniformity exists because Earth is enormous. Its radius is over 6,300 kilometers. Your 10-meter climb represents an almost infinitely small fraction of that distance. Gravity stays effectively the same. Inside a Stanford Torus with a rim radius of 900 meters, the situation is radically different. Stand on the floor and you feel 1 g, full Earth normal weight, your bones and muscles loaded exactly as they would be on the surface of your home planet. Now climb a ladder 10 meters toward the axis. You have moved roughly 1% of the total radius. Your apparent gravity has dropped by 1%. That sounds small, but keep climbing. Go up 50 meters, 5% of the radius, and gravity has dropped to 95% of normal. Your body noticeably lighter. Continue to 100 meters, and gravity is down to about 89% of Earth normal. At 450 meters, halfway to the axis, you weigh half what you did on the floor. At the axis itself, you are weightless. True 0 g floats in the dead center of a structure whose outer rim feels exactly like standing on Earth. This gradient is permanent and inescapable. It is built into the geometry of rotation, and it creates design challenges that have no parallel in terrestrial architecture. Imagine an apartment building inside the habitat. The ground floor sits on the rim at 1 g. The 5th floor, maybe 15 meters higher, sits at slightly lower gravity. Move a few hundred meters toward the axis, and the feeling shifts from subtle lightness to something resembling a low-gravity world. Residents on different floors of the same building experience fundamentally different physical environments. Water pressure in plumbing systems changes with altitude, because the fluid weighs less at higher floors, so pumps and pipe diameters must be calibrated for a gradient that does not exist in any building on Earth. Staircases become progressively easier to climb as you ascend, not because your muscles are warming up, but because each step lifts objectively less weight. Fire behaves differently at lower gravity levels. Flames change shape, becoming rounder and less directional as buoyancy-driven convection weakens. Smoke rises more slowly, or barely rises at all, which means smoke detectors designed for Earth conditions may not work reliably on upper floors. Emergency sprinkler systems must account for water falling in wider, slower arcs. Sports played on the rim would feel normal. The same sport played 50 meters higher would feel subtly alien, with balls hanging in the air longer and athletes jumping noticeably higher. The gradient also means that no single floor inside the habitat truly replicates the full sensory experience of Earth gravity. On Earth, gravity pulls straight down with uniform intensity regardless of whether you are standing in a basement or on a rooftop. Inside the habitat, gravity pulls toward the rim, and its strength depends on your distance from the axis. A person standing on the rim with their arms raised overhead has slightly less gravity at their fingertips than at their feet. The effect is small for a human-sized body, but it exists, and it compounds with height. A tall building or a deep agricultural terrace spans a range of gravitational intensities that would never vary across the same distance on a real planet. Engineers can use this gradient deliberately. The O'Neill cylinder design placed agriculture in a separate outer ring, rotating at a different rate to optimize growing conditions. Some modern concepts propose placing heavy industry and manufacturing near the axis where low gravity makes handling massive components easier. The Kalpana 1 design includes inner cylinders at reduced gravity levels for agriculture, storage, and industrial work. 0 g manufacturing at the hub could produce materials impossible to create under full gravity. Perfect crystal structures, ultra-pure alloys, foamed metals with specific porosity patterns. The gradient is simultaneously a challenge and a resource, but the physiological unknowns are deeply troubling. No human being has ever lived under sustained partial gravity. We have extensive data on microgravity, from the International Space Station bone loss of roughly 1 to 2% per month, muscle atrophy, fluid redistribution toward the head, cardiovascular deconditioning, vision problems from increased intracranial pressure, and we have extensive data on full Earth gravity that is simply normal life. What we lack almost entirely is data on the space between. Does living at 90% of Earth gravity prevent bone loss? Does 80% suffice? 70%? Where is the threshold below which the human body begins to deteriorate? Nobody knows. Not with confidence. Not with the kind of certainty you need before committing 10,000 people to a permanent home, where gravity is a gradient rather than a constant. Children are an even greater concern. A child growing up on the rim of a rotating habitat experiences 1G on the playground, but significantly less if they visit a friend's family on a higher floor. Their developing bones, muscles, and cardiovascular systems are calibrated by the gravity they experience during growth. If a child spends significant time in the reduced gravity zones of the habitat, will their skeleton develop properly? Will their heart grow strong enough for full gravity? Will they be able to visit Earth someday without collapsing under a weight their body was never fully trained for? These questions have no answers because the experiments have never been run. They cannot be run on Earth, and they have never been run in space. This is the first hard truth of habitat physics. You are building a world whose most fundamental physical feature, gravity, varies across the interior, cannot be made uniform, and has never been tested for long-term human habitation. Every rotating habitat design is, at some level, an experiment on the people living inside it. Now consider what is trying to kill those people from outside the walls. Space is saturated with radiation. Not the gentle warmth of sunlight, though that is radiation too, the lethal kind. The kind that passes through metal, through flesh, through bone, and tears apart the molecular bonds in your cells. Two sources dominate the deep space radiation environment, and both are relentless. The first is galactic cosmic rays. These are not rays in the colloquial sense. They are individual atomic nuclei, mostly hydrogen nuclei, which are single protons, along with helium nuclei and a scattering of heavier elements, up to and including iron stripped of their electrons, and accelerated to enormous energies by processes in distant supernova remnants and other violent astrophysical events. These particles travel through the galaxy at velocities approaching the speed of light. A single iron nucleus moving at close to the speed of light is smaller than an atom, yet it punches through centimeters of metal and deposits enough concentrated energy along its path to shatter thousands of molecular bonds in every cell it crosses. When this particle hits the wall of your habitat, it does not simply stop. It smashes through the material, shattering atomic nuclei along its path, generating a spray of secondary particles, neutrons, protons, pions, gamma rays that fan out into the interior. Even after passing through centimeters of metal, the primary particle may still be moving fast enough to penetrate a human body and damage cells along a narrow track of ionization. Galactic cosmic rays are always present. They come from every direction simultaneously. They do not follow schedules. They cannot be predicted or avoided. They do not stop during sleeping hours or meal times or holidays. And they deliver a slow, continuous dose of ionizing radiation to anyone not protected by significant mass or a strong magnetic field. The biological damage accumulates over months and years. High-energy particles passing through living tissue break chemical bonds in DNA, causing mutations that can lead to cancer years or decades later. They damage the lining of blood vessels, increasing long-term cardiovascular disease risk. They strike the lens of the eye, causing cataracts. Recent research suggests they may damage neural tissue in ways that impair cognitive function, memory, decision-making. Spatial reasoning effects, sometimes called space brain, in informal discussions among researchers. The damage is statistical. No single particle guarantees illness, but every particle adds to a cumulative probability that climbs steadily over time. On Earth's surface, the atmosphere and the planetary magnetic field reduce the galactic cosmic ray dose to a small fraction of what exists in open space. In low Earth orbit, inside the magnetosphere, the dose is higher but still partially shielded. In deep space at the L5 point where the Stanford Torus would orbit, or anywhere outside Earth's magnetic protection, the full, unshielded galactic cosmic ray flux delivers roughly 600 to 1,000 millisieverts per year. For context, The recommended annual dose limit for radiation workers on Earth is typically 20 millisieverts. An unshielded person in deep space receives 30 to 50 times that occupational limit every single year. Over a decade, the accumulated dose would virtually guarantee significant health consequences. Over a lifetime, it would be devastating. The second source is solar particle events. These are bursts of energetic protons and heavier ions ejected by the sun during solar flares and coronal mass ejections. Unlike galactic cosmic rays, which arrive as a steady drizzle, solar particle events come as sudden storms. A major event can deliver a potentially lethal dose more than 1 full sievert in a matter of hours. During the August 1972 solar storm, which occurred between the Apollo 16 and Apollo 17 missions, the estimated dose for an unprotected astronaut on the lunar surface would have been several sieverts. That is enough to cause acute radiation sickness and could be fatal without immediate medical treatment. Astronauts on the surface during that event would have been in serious danger. The habitat must stop both sources, and the physics of stopping them is not intuitive. You might assume that more shielding is always better. Pile on enough material and the radiation cannot get through. This is approximately true for solar particle events, whose protons typically have energies in the range of tens to hundreds of millions of electron volts. A meter or two of dense material stops most of them effectively, but for galactic cosmic rays, which can carry energies of billions of electron volts per nucleon, the story takes a disturbing turn. When a high-energy galactic cosmic ray particle strikes a shield made of heavy atomic nuclei aluminum, iron, titanium, it can shatter those nuclei in a process called spallation. The collision produces a cascade of secondary particles, particularly neutrons, that spray into the material behind the impact point. Neutrons are biologically dangerous because they carry no electric charge and therefore pass easily through most matter, depositing energy in tissue along the way. The cruel irony is that for certain thicknesses of metal shielding, the secondary neutron dose actually exceeds the dose you would have received with no shielding at all. You build a wall to protect your crew, and the wall makes things worse. Research using radiation transport codes has shown that for aluminum shielding, the dose equivalent from galactic cosmic rays initially decreases over the first 20 grams per square centimeter of material, then begins rising as secondary neutron production overwhelms the primary particle attenuation. There is a local minimum, an optimal thickness, beyond which adding more aluminum is counterproductive. This finding fundamentally altered the shielding design paradigm. You cannot simply pile on metal until the problem goes away. The solution is hydrogen-rich shielding material. When high-energy particles strike hydrogen nuclei, single protons, the spallation effect is minimal, because there is no heavy nucleus to shatter. The incoming particle loses energy through repeated collisions with light nuclei without generating dangerous secondary cascades. Water, polyethylene, and other hydrogen-dense materials provide significantly more radiation protection per unit mass than metals. The best shields combine structural material on the outside with thick layers of hydrogen-rich material on the inside. But even optimized shielding requires enormous mass. Rotating habitat studies have consistently found that safe permanent shielding against galactic cosmic rays requires several tons of mass per square meter of hull surface, the equivalent of burying the entire habitat under roughly 2 meters of crushed lunar rock on every exposed face. At that depth, galactic cosmic ray doses drop to levels comparable to natural background radiation on Earth's surface. Safe for permanent habitation, safe for raising children, but the mass cost is staggering. The Stanford Torus has an exterior hull area of roughly 2 square kilometers. Packing several tons of processed regolith onto every square meter of that hull accounts for the approximately 9.5 million tons of shielding mass established earlier. The reason, 95% of the case, habitat's total mass is armor. The livable volume is a thin pocket of breathable space buried inside a mountain of processed rock. Could you use magnetic shielding instead of mass? Theoretically, a sufficiently powerful magnetic field could deflect charged particles the way Earth's magnetosphere deflects the solar wind and most cosmic ray particles. But the engineering requirements are prohibitive at habitat scale. Deflecting galactic cosmic rays with energies of billions of electron volts requires magnetic field strengths and spatial extents that no superconducting system has ever achieved in any application, terrestrial or orbital. Proposals exist on paper, Research groups have studied superconducting solenoid configurations that could provide meaningful protection against solar particle events, which carry lower energies than galactic cosmic rays. But full galactic cosmic ray protection via magnetic shielding remains beyond current or near-term technology. For the foreseeable future, mass is the shield, and mass is heavy, and heavy costs everything. Now comes the problem that almost nobody talks about, the one that habitat designers sometimes call the silent killer. It receives a fraction of the public attention given to radiation or gravity, but among engineers who have actually worked on habitat thermal budgets, it is often considered the single most constraining design factor. Every watt of energy used inside the habitat eventually becomes heat. Every single watt. There are no exceptions to this law. Conservation of energy guarantees it. The electrical power that lights the agricultural zones becomes heat when the light is absorbed by plants, soil, and surfaces. The power that runs the air recycling compressors becomes heat through friction in the fans, pumps, and motors. Human metabolism converts food into body heat at a rate of roughly 100 watts per person at rest. More. During physical activity add up 10,000 people, and that is 1 megawatt of continuous thermal load just from human beings existing and breathing. The computing systems generate heat. The manufacturing equipment generates heat. The water treatment plants, the communication arrays, the kitchen appliances, the laundry systems, every device that draws electrical power converts that power into useful work and waste heat, and even the useful work eventually degrades into heat through friction, absorption, and dissipation. In a closed system, energy has nowhere to go except into the thermal budget. On Earth, waste heat is not a crisis because the planet has an atmosphere and hydrosphere that act as enormous thermal buffers. Hot air rises, cool air descends. Convection carries heat away from its source. Water evaporates from oceans and lakes, absorbing vast quantities of thermal energy and releases that energy elsewhere when it condenses into clouds and rain. Wind distributes thermal energy across continents and oceans. Rivers carry heat downstream. Ultimately, Earth radiates its total excess heat into space from the upper atmosphere, maintaining a dynamic thermal equilibrium across the entire planetary surface. We take this thermal management system for granted because it operates at a scale so massive and so silent that we never notice it working. In the vacuum of space, none of these mechanisms exist. There is no air outside the habitat to carry heat away through convection. There is no ocean to serve as a thermal sink. There is no wind, no evaporation, no rain. The vacuum of space is a nearly perfect insulator, the same principle that makes a vacuum thermos bottle keep coffee hot for hours. A habitat in space is essentially a thermos bottle turned inside out. The vacuum that surrounds it prevents heat from escaping through any mechanism except one. The only way to lose heat in a vacuum is thermal radiation, electromagnetic energy, emitted by any surface at a temperature above absolute zero. This is the same process that makes a hot coal glow red in a dark room, or makes the heated element of a toaster radiate warmth across a kitchen. Every object radiates energy proportional to the fourth power of its absolute temperature and to its surface area and emissivity. This relationship, described by the Stefan Boltzmann law, creates a stark engineering reality. High temperature waste heat radiates efficiently. Low temperature waste heat radiates miserably. But here is the engineering trap. Most of the waste heat inside a habitat is generated at relatively low temperatures. Room temperature, roughly 300 Kelvin. Heat from life support systems, from human bodies, from agricultural lighting, from electronics. All of it arrives at temperatures between 280 and 320 Kelvin. At those temperatures, each square meter of radiator surface emits only about 450 watts. That is the fundamental bottleneck. Low temperature heat is incredibly difficult to radiate away because the physics demands enormous surface areas to handle even modest thermal loads. Run the numbers for a city-sized habitat. Suppose the combined thermal load from power systems, sunlight absorption, metabolic heat, agriculture, and industry totals 200 megawatts. That is a conservative estimate for a habitat of 10,000 people with agricultural and light industrial capacity. At 300 Kelvin and an emissivity near 1, each square meter of radiator rejects roughly 450 watts from a single face. or about 900 watts if both sides of a flat panel radiate freely into space. To reject 200 megawatts, you need approximately 220,000 square meters of radiator surface. That is more than 0.2 square kilometers. For scale, the entire interior habitable surface of the Stanford Torus is about 6.5 square kilometers. The radiator array needed to cool the habitat approaches a significant fraction of the habitat's own size, and those radiators cannot be hidden. They must face open space, aimed away from the sun, away from any warm surface, pointed at the cold void so their emitted radiation escapes without being reflected or reabsorbed. If a radiator panel faces the sunlit side of the habitat, it absorbs solar energy instead of rejecting waste heat, which defeats the purpose entirely. Radiator panels must be carefully oriented perpendicular to the sun line or deployed in shadowed regions behind the habitat's mass. This orientation constraint creates the habitat's most terrifying vulnerability. The radiators are the one major system that cannot be buried behind shielding. The shielding protects the crew from radiation. The structural shell contains the atmosphere. The rotation mechanism is integral to the hull. But the radiators must be exposed to the vacuum. They must have unobstructed lines of sight to empty space. They are, by the fundamental physics of their operation, the most exposed and least protected component of the entire structure. A micrometeorite impact on a radiator panel could puncture coolant lines, causing fluid leaks that degrade thermal rejection capacity. A large enough impact could disable an entire radiator section, and if the habitat cannot reject its waste heat, temperatures inside begin climbing, not instantly. Thermal mass provides a buffer, hours or perhaps days, depending on the habitat's size and insulation properties, but the trajectory is inexorable. Without repair, the interior temperature rises until life support systems begin failing, crops begin dying, and the habitat becomes uninhabitable. Heat stroke and system cascading failures would follow. Walk through the timeline of a thermal emergency to understand why this threat is so insidious. Suppose a debris impact disables 30% of the habitat's radiator capacity in a single event. In the first hour, nothing perceptible happens. The interior temperature does not change. The air feels the same. People go about their routines. This is because the habitat has thermal mass, millions of tons of steel, rock, water, and soil that absorb heat slowly, the way a concrete building stays cool on the first hot morning of summer, even before anyone turns on the air conditioning. The thermal buffer buys time, but it does not buy a solution. By hour 6, sensors register the first measurable temperature increase. Half a degree, perhaps a full degree. Still within the comfort band, still ignorable by anyone not watching the monitoring screens. But the trend line is climbing, and it is not going to stop. The habitat is generating the same amount of waste heat it always does from power systems, from human metabolism, from agricultural lighting, from every machine that draws current, and 30% of its ability to shed that heat into space is gone. The energy has nowhere to go except into the interior. By hour 24, the temperature has risen several degrees. Humidity climbs as warmer air holds more moisture. Condensation forms on cool surfaces, pipes, structural members, equipment housings. Electronics designed to operate within narrow temperature bands begin reporting anomalies. Agricultural crops, many of which are sensitive to temperature swings of just a few degrees, show the first signs of heat stress. Wilting leaves, slowed growth, increased water demand from soil that is drying faster than the irrigation system was calibrated to handle. By hour 48, the interior feels like a heat wave that will not break. The habitat's controllers face triage decisions that have no good answers. They can reduce the thermal load by shutting down non-essential systems, dimming agricultural lighting, powering down manufacturing equipment, suspending some water recycling processes. But every system they shut down also reduces the habitat's capacity to function. Dimming the grow lights slows food production. Shutting down manufacturing halts spare part fabrication. Suspending water recycling depletes clean water reserves. The controllers are choosing which capabilities to sacrifice now to delay a worse crisis later. By hour 72, if repairs have not restored radiator capacity, the temperature approaches the operating limits of critical life support hardware. Air recycling compressors overheat. Cooling pumps strain against fluid that is warmer than designed. Power electronics derate themselves, reducing output to avoid thermal damage. The habitat is running a fever it cannot break, and every system that fails from overheating adds its waste heat to the problem, while simultaneously removing its function from the survival equation. The cascade has begun. The clock is no longer measured in hours. It is measured in the number of systems that fail before the repair crew can restore what was lost. The International Space Station provides a sobering reference point. Its external thermal control system uses ammonia-based coolant loops circulating through approximately 1,400 square meters of radiator panels to reject roughly 70 kilowatts of internal waste heat. That system has experienced coolant leaks requiring emergency spacewalk repairs. On a city-sized habitat, the radiator system would be orders of magnitude larger, handling thousands of times more thermal energy, and a repair crew could not simply step outside in a spacesuit to patch a leak on a structure spinning at 1 revolution per minute, while radiator panels extend hundreds of meters from the hull. Redundancy helps. Multiple independent cooling loops ensure that the failure of one circuit does not cascade into total thermal failure. Segmented radiator panels allow damaged sections to be isolated while others continue operating. Spare capacity built into the system provides margin for partial failures, but redundancy adds mass, complexity, and additional failure modes. Each backup system requires its own plumbing, its own pumps, its own control hardware. Each added component is one more thing that can eventually break, and this is where the three constraints become a trap that tightens with every design iteration. More shielding mass protects against radiation but increases the structural load the rotating shell must bear, pushing the habitat closer to its hoop stress limit. Strengthening the structure to carry more shielding requires thicker walls, which add mass of their own, which increases hoop stress further, generating more electrical power for life support. Agriculture and manufacturing produces more waste heat, which demands larger radiator arrays, which increases the habitat's exposed surface area and vulnerability to impacts. Spinning the habitat faster to compensate for a smaller radius increases Coriolis effects and structural stress. Slowing the rotation to improve comfort requires a larger radius, which requires more structural material and more shielding surface area, which increases total mass, which increases hoop stress again. Every parameter is coupled to every other parameter. There is no slack in the system. Solving one constraint tightens another. The habitat designer is not solving a single engineering problem. They are solving a system of simultaneous equations, where the variables are mass, radius, rotation rate, shielding thickness, power generation, thermal rejection area, and structural strength, and every variable pushes against at least two others. This is why no one has ever built a city-sized spaceship, not because the individual physics problems are unsolvable. Each one has known solutions. Rotation produces gravity. Mass stops radiation. Radiators reject heat. The solutions exist. The impossible part is making all the solutions fit inside the same object, at the same time, within mass and structural limits that leave zero room for error. The habitat is not an engineering project. It is an engineering negotiation between constraints that do not want to coexist. And yet, everything described so far assumes you already have the materials to build with. It assumes the steel, the regolith, the aluminum, the coolant fluid, the glass, the structural composites are all sitting at the construction site, ready for assembly. In reality, none of it is there. Every gram of material must be extracted from a celestial body, processed in a facility that does not yet exist, transported to a location where no factory has ever operated, and assembled by methods that have never been demonstrated at scale. We established that the material cannot come from Earth. The gravity well is too deep, the mass too great, the cost too ruinous. The material must come from space itself, from the moon, from asteroids, from wherever raw resources can be obtained without paying the energy tax of climbing out of a planetary gravity well. But identifying the source is not the same as building the supply chain. Mining lunar regolith is not the same as mining coal in Pennsylvania. Smelting iron from an asteroid is not the same as operating a blast furnace in Pittsburgh. Assembling a 10 million ton rotating structure in vacuum and microgravity is not the same as bolting together a bridge over a river. What comes next is the story of how you would actually extract, process, transport, and assemble the material for a city-sized habitat and why that story requires an industrial revolution that has not yet begun. The physics are understood. Rotation produces gravity. Mass stops radiation. Radiators reject heat. These are not mysteries. They are constraints, brutal and non-negotiable. But they are known. The equations are written. The material properties are tabulated. The engineering trade-offs are mapped. What remains is a question that sounds simple and turns out to be the hardest part of the entire project. Where do you get 10 million tons of construction material when you cannot launch it from Earth? Everything discussed so far establishes that the habitat's mass makes Earth-based launch absurd. But dismissing Earth as the source only clears the first obstacle. You still need to find raw material in space, extract it, refine it, transport it to the construction site, manufacture it into structural components, and assemble those components into a spinning, pressurized habitat, all using industrial processes that have never been performed at scale outside a planetary surface. This is not merely an engineering challenge. It is an industrial revolution that must happen in a vacuum, in microgravity, with no existing supply chain, no trained workforce, no spare parts depot, and no second chances. The 1975 Stanford Torus study did not ignore this problem. It confronted it head-on and produced a construction plan that remains, 50 years later, the most detailed blueprint ever drafted for building a large space habitat. The plan begins not in orbit, but on the moon. Lunar regolith, the powdery, rocky material covering the moon's surface to depths of several meters, is an unexpectedly rich feedstock. It is not dirt in the terrestrial sense. It is pulverized rock, created over billions of years by micrometeorite impacts, grinding the lunar surface into fine particles. Its composition reflects the minerals of the lunar crust, roughly 45% oxygen by mass, bound chemically into metal oxides, 21% silicon, 6 to 14% iron depending on location, 5 to 13% aluminum, significant quantities of calcium, magnesium, and titanium. These are not exotic elements. They are the same materials that form the backbone of terrestrial industry, the same elements found in steel, aluminum alloys, glass, and concrete. The moon's surface is, in essence, an unprocessed industrial feedstock spread across millions of square kilometers, sitting at the top of a gravity well only 1/6 as deep as Earth's. The Stanford study proposed exploiting this feedstock through a system of electromagnetic mass drivers built on the lunar surface. A mass driver is conceptually straightforward. A linear electromagnetic accelerator, essentially a long track of sequential magnetic coils that accelerate small buckets of material to high velocity along a precisely aligned rail. Each bucket carries a payload of processed regolith, perhaps 10 to 20 kilograms per shot, and is accelerated along the track until it reaches lunar escape velocity, roughly 2.4 kilometers per second. The bucket does not leave with the payload. At the end of the track, it releases its cargo and decelerates back to the starting position for reloading. The payload, a small dense packet of refined lunar material, sails off into space on a precisely calculated ballistic trajectory toward a collection point hundreds of thousands of kilometers away. The process is repetitive, mechanical, and relentless. A single mass driver operating continuously could launch one payload every few seconds, tens of thousands of packets per day, each one arcing silently away from the lunar surface on a trajectory computed to arrive at the collection point days later. No rocket fuel is consumed. No exhaust is produced. The energy comes from solar panels spread across the lunar surface, converting sunlight into the electromagnetic pulses that drive each bucket along the track. The moon becomes a factory whose conveyor belt is a beam of magnetically launched rock. Gerard O'Neill and his colleagues at Princeton built working prototype mass drivers in the late 1970s. They demonstrated the core principle: electromagnetic acceleration of payloads along a track using sequentially pulsed coils. The prototypes were small, laboratory-scale devices, accelerating payloads of a few hundred grams over a few meters. But they proved the physics worked. The acceleration profile matched predictions. The energy efficiency was within the range needed for lunar operations. A full-scale lunar mass driver would be a structure, perhaps several kilometers long, built on the moon's surface near a processing plant, powered by solar arrays spanning hectares of regolith, and operated entirely by robotic systems. It would launch thousands of payloads per day, each one a small packet of processed regolith or extracted metal, into a trajectory aimed at a collection point in cislunar space. That collection point would house a mass catcher, a large, lightweight structure designed to intercept and absorb incoming payloads. The catcher might be a bag of woven fibers, or a magnetic braking system, or a combination of both. It would orbit at the L2 Lagrange point behind the Moon, or be positioned near the L5 construction site. The engineering of the catcher is non-trivial. It must absorb the kinetic energy of thousands of impacts per day without being destroyed, but it does not require fundamentally new physics. It requires robust materials, science, and careful trajectory control. Once the raw material reaches the orbital processing facility, the real transformation begins. Lunar regolith in its raw state is not construction material. It is mixed oxide powder. Turning it into structural steel, aluminum sheet, glass panels, or radiation shielding requires industrial chemistry and metallurgy. The same processes that drive terrestrial manufacturing, adapted for operation in vacuum and microgravity. Solar furnaces would provide the heat. In space, with no atmosphere to scatter or absorb light, solar energy can be concentrated to extraordinary intensities using nothing more than curved mirrors. A parabolic mirror only a few meters across can focus sunlight into a spot hot enough to melt steel. Imagine a magnifying glass the size of a house, aimed at a crucible of lunar ore, with the full unfiltered power of the sun concentrated into a point no larger than a coin. Larger concentrator arrays tens or hundreds of meters in diameter could generate temperatures exceeding 2000 degrees Celsius, sufficient for smelting iron from oxide ores, melting glass from silica, or refining aluminum from its mineral precursors. The energy source is free, unlimited for practical purposes, and requires no fuel shipments. The Sun delivers roughly 1360 watts per square meter at Earth's orbital distance, and it never stops. A concentrator array 100 meters in diameter captures over 10 megawatts of continuous thermal power. That is a serious industrial furnace, powered entirely by light, with an energy bill of zero and a fuel supply that will last another 5 billion years. The refining processes themselves would resemble terrestrial metallurgy adapted for alien conditions. Iron can be extracted from lunar ilmenite, an iron titanium oxide mineral common in the darker mare basalts, by heating it with hydrogen gas. The hydrogen bonds with the oxygen in the ore, producing water vapor and leaving metallic iron and a titanium-rich oxide residue behind. The captured water is then split through electrolysis to recover free oxygen, because oxygen is itself one of the most valuable products of lunar processing. It provides breathable atmosphere for habitats, oxidizer for rocket propellant, and a component of water when combined with hydrogen. Aluminum can be extracted from a northite, a calcium-aluminum silicate abundant in the lunar highlands, through electrolytic reduction, a process similar in principle to how aluminum is produced on Earth, but performed in vacuum using solar-generated electricity. Silicon can be refined from silica for use in glass panels, semiconductor wafers, and solar cells. The lunar surface provides the raw ingredients for an entire industrial materials chain. What it does not provide is the factories to run that chain. Vacuum itself becomes an asset. On Earth, metallurgical processing must fight oxidation, the tendency of hot metals to react with atmospheric oxygen, forming rust, scale, and impurities. In the vacuum of space, there is no atmospheric oxygen. Metals can be melted, alloyed, cast, and cooled without oxidation. The resulting products are purer than anything achievable in terrestrial foundries without expensive inert gas atmospheres. Vacuum welding, vacuum casting, and vacuum annealing become default conditions rather than costly special procedures. Microgravity offers additional manufacturing advantages. On Earth, gravity causes density-driven separation in molten materials. Heavier components sink, lighter ones float, creating compositional gradients that weaken the final product. In microgravity, this segregation does not occur. Alloys can be mixed with perfect uniformity. Foamed metals' metallic structures containing controlled internal voids that combine low density with high strength can be produced with bubble distributions impossible to achieve under gravity. Single crystals can be grown to sizes and perfection levels unattainable in ground-based laboratories. These are not theoretical benefits. Experiments aboard the International Space Station have demonstrated improved crystal growth and alloy formation in microgravity over more than 2 decades. But here is where optimism collides with reality. Every process just described, mass driving, regolith collection, solar smelting, vacuum metallurgy, microgravity manufacturing, has been demonstrated either in laboratory prototypes or in small-scale orbital experiments. None has been demonstrated at industrial scale. The gap between a prototype mass driver launching a 1-kilogram payload across a university laboratory and a full-scale lunar installation launching 20,000 tons of material per year is not merely quantitative, it is qualitative. It involves problems of thermal management, mechanical wear, dust contamination, power distribution, automated maintenance, quality control, and logistical coordination that do not appear until you scale the process by factors of thousands. The current state of in-space manufacturing illustrates both how far the technology has come and how far it has yet to go. As of 2026, the first orbital foundries are beginning operation. Small-scale facilities in low Earth orbit producing high-value materials like ultra-pure fiber-optic cable preforms and protein crystals that benefit from microgravity processing. These are real products with real commercial value, but they are measured in grams, not tons. The entire output of every orbital manufacturing facility currently in operation could fit inside a single suitcase. Scaling from suitcase quantities to the millions of tons required for a habitat is a journey measured in decades of industrial development, not years of incremental improvement. Asteroid mining tells a similar story of promise and distance. Near-Earth asteroids represent an almost inconceivably rich source of construction material. They come in 3 broad categories. C-type asteroids, the most common, are carbonaceous, rich in water ice, carbon compounds, and clay minerals. Their water content alone is enormously valuable because water provides both radiation shielding mass and, through electrolysis, oxygen for breathing and hydrogen for fuel. S-type asteroids are silicaceous, containing silicate minerals along with metallic iron and nickel, similar in some respects to rocky planetary material. M-type asteroids are metallic, composed primarily of iron and nickel, with traces of precious metals including platinum, cobalt, and gold. A single M-type asteroid, 500 meters in diameter, might contain more accessible iron and nickel than humanity has extracted from Earth's crust in all of recorded history. From an orbital mechanics perspective, many near-Earth asteroids are surprisingly accessible. The change in velocity delta V required to reach some near-Earth asteroids from low Earth orbit is actually less than the delta V required to land on the Moon. This means that, energetically speaking, some asteroids are closer than the lunar surface. You burn less propellant getting there. The material is effectively sitting on a lower shelf than the Moon, at least in terms of the rocket fuel required to reach it. But reaching an asteroid and mining it are fundamentally different activities. An asteroid is not a stationary quarry with solid ground underfoot. Most near-Earth asteroids are small, irregularly shaped bodies with surface gravities so feeble that a person could jump to escape velocity with a modest hop. There is no traction. There is no down. Drilling into the surface would push the drill away from the rock rather than into it. An excavator designed for terrestrial mining would simply float off the surface the moment it tried to dig. Every tool, every technique, every procedure must be reinvented for an environment where the object you are mining barely holds itself together and provides almost no gravity to work against. The first commercial deep space asteroid prospecting mission, launched in early 2025, aimed to fly past a near-Earth asteroid and assess its composition using onboard sensors. The spacecraft experienced significant communications and attitude control failures shortly after launch and did not complete its planned flyby. A follow-up mission is being prepared for launch in 2026 or 2027. Even if this next mission succeeds in reaching its target and returning compositional data, it will represent only the earliest step in a chain that must eventually include orbital approach, surface anchoring on a body with negligible gravity, material extraction using fully autonomous equipment, processing either in situ or at a nearby orbital facility, and delivery of refined product to the construction site. Each step involves unsolved engineering problems at operational scale. The gap between photographing an asteroid during a flyby and operating a self-sustaining mine on its surface is comparable to the gap between photographing the ocean floor from a boat and operating a deep-sea oil rig. The material science question adds another layer of constraint. You cannot simply choose the ideal construction material and order it delivered. You must build with whatever you can actually produce from the feedstock available. And different feedstocks yield different materials with different structural properties. Steel iron alloyed with small amounts of carbon is the most familiar structural material in human history. It is strong, well understood, and its long-term fatigue behavior has been studied for over a century. We know exactly how steel behaves under sustained stress, how it corrodes, how it fails, and how to inspect it for damage. This institutional knowledge is enormously valuable for a structure that must last decades or centuries. But steel is dense. Its high density means that a steel habitat shell contributes heavily to hoop stress, limiting the maximum radius of the structure. A steel O'Neill cylinder pushes close to the theoretical breaking limit for the material. Aluminum is lighter than steel and offers a better strength-to-density ratio, which means lower hoop stress for a given radius. Aluminum alloys are used extensively in aerospace construction, but aluminum is more susceptible to fatigue cracking over long time periods and is more difficult to inspect for internal flaws. In a structure that must maintain pressure integrity for decades, undetectable fatigue cracks are a nightmare scenario. Basalt fiber is a compelling option for space construction because basalt, a volcanic rock rich in silica, iron and aluminum oxides, is abundant in both lunar regolith and many asteroid compositions. Basalt can be melted and drawn into fine fibers with tensile strength comparable to or exceeding that of glass fiber. These fibers can be woven into fabrics, wound into composite structures, or used as reinforcement in concrete-like matrices. Basalt fiber production requires only heat and raw rock, both available in abundance in space. Its strength-to-density ratio is competitive with steel, and its raw material does not require complex chemical processing. Anhydrous glass, glass produced in the absence of water, has been proposed as a primary structural material for lunar-sourced habitats. Lunar regolith can be melted and cast into glass panels or drawn into fibers with very high tensile strength, exceeding 1500 megapascals in some formulations. Glass in space does not face the surface moisture degradation that weakens glass on Earth. When produced and maintained in vacuum, anhydrous glass retains its full theoretical strength indefinitely. Some habitat design studies have proposed truss-like structures made from glass regolith composites as the primary load-bearing framework, with raw regolith packed into the interstices as radiation shielding and agricultural soil. Carbon fiber composites offer the best strength-to-density ratio of any practical structural material, which is why they dominate high-performance aerospace construction on Earth. But carbon is relatively scarce in lunar regolith. Producing carbon fiber from space resources would require either carbonaceous asteroid material or chemical extraction processes that are energy-intensive and complex. For a habitat built primarily from lunar feedstock, carbon fiber is likely available only in limited quantities for critical high-stress components, rather than as the primary structural material. The real answer to the material question is almost certainly a composite approach. Glass and basalt fiber structures produced from lunar or asteroidal regolith, reinforced at high stress points with metals refined from the same feedstock, with carbon composites used sparingly where no other material suffices. The habitat will be built from whatever the available supply chain can actually produce in the required quantities, not from whatever material an engineer on Earth might prefer. This leads to the deepest practical problem in the entire construction chain, the bootstrapping paradox. To build the habitat, you need an orbital manufacturing facility, smelters, rolling mills, fabrication equipment, assembly robots. To build that facility, you need raw material from the moon or an asteroid. To get that material, you need a mining operation on the lunar surface, excavators, processors, mass drivers, power stations. To build and operate that mining base, you need workers. To keep those workers alive, you need habitats, life support systems, food, water, and medical facilities. To supply those habitats, you need a transportation system. To build the transportation system, you need manufacturing capability, which is the thing you are trying to build in the first place. Every link in the chain depends on a link that does not yet exist. You cannot build the ship without the shipyard. You cannot build the shipyard without the port. You cannot build the port without the road. And you cannot build the road without the ship to bring the workers. The circle is vicious, and it cannot be broken from any single point. It must be broken from outside from Earth using the most expensive approach possible, launching finished equipment, supplies, and personnel from the bottom of a deep gravity well on chemical rockets. This is the one phase of the project where launch cost cannot be avoided. Every ton sent to the moon to establish the initial mining base must be paid for at full price. The entire purpose of the lunar industrial infrastructure is to ensure that this brutal launch cost is paid only once, at the beginning, and never again at the same scale. The 1975 Stanford study proposed a phased approach to break this circle. Phase 1. Establish a small lunar surface base using material and personnel launched entirely from Earth. This is the only phase that relies on terrestrial launch capability for structural mass, and it is by far the most expensive per ton of delivered material. The base would be minimal pressurized habitats for a few dozen workers, solar power arrays, regolith excavation equipment, a processing plant to sort and refine the raw material, and the first segments of the mass driver track. The base would not be comfortable. It would not be spacious. It would exist for one purpose: to start the pipeline of material flowing off the lunar surface and into space. Phase 2. Begin launching processed regolith from the lunar surface to the L5 construction site using the mass driver. Simultaneously, a temporary orbital work camp far smaller and simpler than the final habitat would be assembled at L5 to house the construction crew. This camp would resemble a scaled-up space station rather than a city. Dozens of workers, not thousands. Cramped quarters, recycled air, limited food variety. It would be supplied from Earth initially but would transition to lunar-sourced consumables as the supply pipeline matures. The workers at this camp would assemble the orbital processing equipment, the solar furnaces, the smelters, the rolling mills and fabrication systems using material arriving from the moon. Phase 3. The orbital manufacturing facility reaches operational capacity. Now the raw material from the moon can be converted into finished structural components at L5. Steel beams, aluminum panels, glass sheets, regolith composite trusses. The facility grows as its own output enables expansion. It builds extensions of itself using the material it processes. This is the critical phase where the project transitions from Earth-dependent to self-sustaining. Once the orbital factory can produce structural material faster than it wears out, the construction of the habitat itself can begin in earnest. Phase 4. Construct the habitat. First, the primary structural frame, the load-bearing skeleton that will support the rotating shell. Then the hull panels bolted or welded to the frame. Then layer after layer of radiation shielding, packed onto the interior surface. Then the atmospheric seal, the final barrier between breathable interior and lethal vacuum. Then the interior build-out, plumbing, electrical systems, lighting, thermal management hardware, agricultural infrastructure, residential structures, transportation networks, docking facilities. Each system is installed, tested, and integrated before the next layer begins. The study estimated a total construction timeline of roughly 6 to 10 years from the start of lunar surface operations to a completed, habitable Stanford Torus. The construction workforce at L5 would peak at roughly 2,000 people, with a total space-based workforce of approximately 6,500 across all operations including lunar mining. The total cost, in 1977 dollars, was estimated at approximately $200 billion, several times the cost of the entire Apollo program, and one of the largest single engineering investments ever seriously proposed, spread over a longer time frame. These numbers have been debated, revised, and critiqued for half a century. Some analysts consider them wildly optimistic. Others argue that modern advances in robotics, autonomous systems, and reusable launch vehicles make the project more achievable than it was in the 1970s. The honest assessment is that nobody knows with certainty, because the critical enabling technologies, large-scale lunar surface mining, electromagnetic mass launching at industrial throughput, orbital smelting and refining of raw regolith, autonomous robotic assembly of pressurized rotating structures, have never been demonstrated beyond prototype or laboratory scale. The knowledge gap between demonstrated capability and required capability remains wide. What we do know is that every required technology rests on established physics. Mass drivers work, solar furnaces work, vacuum metallurgy works, robotic assembly works. In controlled environments, 3D printing of structural components from regolith simulants has been demonstrated in laboratory settings on Earth and in brief microgravity experiments. NASA's Moon to Mars Planetary Autonomous Construction Technologies project is actively testing how lunar soil simulants behave under various processing and printing methods. In early 2025, a test flight aboard a suborbital vehicle simulated lunar gravity conditions to study how regolith flows and settles, comparing simulant behavior against real lunar samples from the Apollo missions. The results feed into construction planning for eventual lunar surface infrastructure. The European Space Agency's in-space manufacturing program has tested concepts for assembling satellite components in orbit, aiming toward a future where complex structures are fabricated in space rather than launched from the ground. Private companies are developing expandable habitat modules that pack into small launch fairings and inflate to many times their launch volume once in orbit, vastly reducing the number of launches needed to create habitable space. One company completed a successful full-scale burst pressure test of an inflatable habitat module in 2024, exceeding NASA safety margins by 27%. Another firm plans to launch a 20 cubic meter expandable demonstration module on a rideshare mission in 2026 to verify deployment and pressure retention in orbit. These are real developments. They represent genuine, measurable progress toward the industrial capabilities that large-scale space construction will eventually require. But they also represent the embryonic stage of a supply chain that must grow by many orders of magnitude before a city-sized habitat becomes feasible. The distance between inflating a single habitat module in low Earth orbit and assembling a 10 million ton rotating structure at the L5 point is comparable to the distance between the Wright brothers' first flight at Kitty Hawk and the construction of a modern international airport with passenger terminals, fuel depots, air traffic control systems, maintenance hangars, and ground transportation networks serving millions of travelers per year. The Wright Flyer proved the physics of powered heavier-than-air flight. It took another century of infrastructure, industrial development, and institutional knowledge to build the global aviation system. Space construction faces a comparable developmental arc, and it has barely begun its first chapter. And even if all of this succeeds, the mining, the launching, the smelting, the manufacturing, the assembly, you still have nothing more than an empty shell. A pressurized, shielded, structurally sound, thermally managed cylinder or torus spinning in the void. Impressive, historic, and completely lifeless. Because a habitat is not alive until it contains life. Not just people, everything that keeps people alive. The air must be manufactured and sealed inside. The water must be sourced, purified, and distributed. The soil must be created processed regolith, mixed with organic compounds, inoculated with microorganisms, cultivated until it can support plant growth. Seeds must be planted, crops must be grown, pollinators must be introduced, waste decomposition bacteria must be established, nutrient cycles must be initiated and balanced. An entire ecology, soil microbiome, plant community, insect populations, possibly aquaculture, and small livestock must be built from scratch inside engineered walls and then maintained indefinitely, without the stabilizing influence of a planetary biosphere that spent 4 billion years calibrating. Itself, the empty structure is a container. What goes inside it, what makes it a world instead of a warehouse, is what comes next. And it turns out that filling the container is harder than building it. The structure is complete. The hull holds pressure, the shielding stops radiation, the radiators reject heat, the spin generates gravity. From the outside, the habitat looks finished, a vast, slowly rotating cylinder or torus drifting at the L5 point, catching sunlight on its mirrors, its radiator panels glowing faintly in the infrared. An engineer might call it done, but an engineer would be wrong, because right now, the habitat is a tomb. It contains air but no breath. It contains soil but no roots. It contains water, but no current of life flowing through it. The structure is a shell, and a shell is not a world. Making it a world requires building something far more fragile and far more complex than any structural frame or radiation shield. It requires building an ecology, a complete, closed, self-regulating web of biological and chemical processes that converts sunlight, water, carbon dioxide, and mineral nutrients into food, oxygen, and clean water, and does so continuously, reliably, and indefinitely, without any input from outside the walls. On Earth, this system is called the biosphere. It took roughly 4 billion years to evolve. Inside the habitat, it must be assembled from scratch in a matter of months, calibrated by human engineers rather than by deep evolutionary time, and maintained in a state of functional balance that nature achieves through brute redundancy across an entire planet. The fundamental challenge is closing the loop. On Earth, nothing is wasted. Dead organisms decompose. Their nutrients return to the soil. Plants absorb those nutrients, grow, and produce oxygen. Animals eat the plants, breathe the oxygen, and exhale carbon dioxide that the plants absorb again. Water evaporates from oceans, falls as rain, filters through soil, flows into rivers, and returns to the sea. Carbon, nitrogen, phosphorus, sulfur, and dozens of trace elements cycle endlessly through atmosphere, hydrosphere, lithosphere, and biosphere. These cycles are not simple. The nitrogen cycle alone involves bacteria that convert atmospheric nitrogen into ammonia, other bacteria that convert ammonia into nitrites, and then nitrates, plants that absorb the nitrates, animals that eat the plants, decomposers that break down dead tissue and release ammonia again, and still other bacteria that convert some nitrogen compounds back into atmospheric gas. This single nutrient loop involves at least 5 distinct types of microorganism, each performing a step that the others cannot. Remove any one group, and the cycle breaks. Nitrogen accumulates in one form or another, becomes unavailable to plants, and agriculture collapses. On Earth, these cycles operate on a planetary scale with enormous buffering capacity. If one forest burns, the global carbon cycle barely notices. If one river floods, the planetary water cycle absorbs the perturbation without strain. Earth's biosphere is resilient, not because it is elegant, but because it is vast. The sheer volume of atmosphere, ocean, and soil provides enough chemical and thermal buffer to absorb disruptions that would be catastrophic in a smaller system. Inside a habitat, these same cycles must operate in a space smaller than a small town. There is no buffering capacity. There is no redundancy of scale. Every atom of carbon, every molecule of nitrogen, every trace of phosphorus that enters the biological system must stay in the system or be recoverable from wherever it ends up. If carbon dioxide accumulates because microbial decomposition outpaces photosynthesis, the atmosphere becomes toxic. If nitrogen compounds leach out of the agricultural soil faster than nitrogen-fixing bacteria can replenish them, crops fail. If phosphorus, an element essential for DNA replication, cell membrane formation, and energy metabolism in every living organism, is lost from the cycle through incomplete waste processing or chemical binding into insoluble mineral compounds, the entire agricultural system slowly starves. And unlike carbon or nitrogen, phosphorus has no atmospheric phase. Once it drops out of biological circulation, it cannot be recaptured by plants breathing it in. It must be physically recovered from waste streams and returned to the soil, a process that requires energy, chemistry, and precision that nature performs for free across an entire planet. The word self-sustaining gets used casually in discussions of space habitats. It should not. No closed ecological system has ever achieved true self-sufficiency for any meaningful duration. Not on Earth. Not in orbit. Not in any laboratory. The most ambitious attempt was Biosphere 2, a 3.14-acre sealed glass enclosure built in Oracle, Arizona, in the late 1980s. It contained multiple biomes: rainforest, ocean, savanna, marsh, desert, along with an agricultural wing and living quarters for 8 crew members who sealed themselves inside in September of 1991 for a planned 2-year mission. The experiment was intended to demonstrate that a closed ecological system could support human life without material exchange with the outside environment. The results were sobering. Within months, oxygen levels inside Biosphere 2 began dropping. The concentration fell from the normal 21% to roughly 14%, equivalent to breathing at an altitude of roughly 4,000 meters. Crew members experienced chronic fatigue, impaired cognitive function, and difficulty performing physical tasks. The cause was eventually traced to an unexpected interaction. Microorganisms in the soil were consuming oxygen faster than the plants could replace it, and the facility's concrete structures were absorbing carbon dioxide through a chemical reaction that locked oxygen into calcium carbonate. The carbon dioxide was being removed from the air, but the oxygen bound up with it was not being returned. The system was bleeding oxygen into its own walls. Crop yields fell short of projections. The crew experienced persistent hunger throughout the mission, losing significant body weight despite working long hours in the agricultural wing. Some agricultural species failed entirely, while invasive species, particularly certain ant populations that had been inadvertently sealed inside, proliferated uncontrollably, outcompeting carefully selected crops for resources. Aggressive morning glory vines overran trellises and shaded out food plants. Cockroach populations surged in the warm, humid conditions. Pollinators struggled in the altered atmospheric composition. Nutrient cycling in the soil proved far more complex and sensitive than the predictive models had suggested. By the midpoint of the mission, external oxygen had to be pumped in to prevent the crew from suffering serious physiological harm, breaking the seal of the closed system and effectively ending the experiment as a test of true ecological closure. What the technical summaries rarely convey is what the experience felt like from inside. The crew members were not passive observers of a system going wrong. They were living inside it, breathing its failing atmosphere, eating its insufficient harvests. They were hungry for months. Caloric intake dropped well below what the mission plan had specified, and crew members lost measurable body mass over the course of the 2-year enclosure. The low oxygen levels produced persistent headaches, fatigue, and a cognitive fog that made complex decision-making harder, precisely when the failing systems demanded more of it. Interpersonal tensions escalated under the combined pressure of physical discomfort, chronic hunger, and the psychological burden of watching a carefully designed world slowly unravel around them. The crew eventually fractured into factions that disagreed over how to manage the crisis, whether to accept outside intervention, and who bore responsibility for decisions that affected everyone's survival. These were not personality conflicts. They were the predictable social consequences of a small, sealed community facing resource scarcity and existential stress with no possibility of leaving. In a space habitat, the same dynamics would play out at larger scale and with higher stakes, because the nearest exit is not a door to the Arizona desert. It is the vacuum of space. Biosphere 2 was not a failure of engineering in the traditional sense. The structure held, the seals worked, the mechanical systems functioned. What failed was the ecology. The biological systems proved too complex, too interconnected, and too sensitive to initial conditions for human engineers to predict and control with the precision required. The lesson was stark. Closing the loop on even a small Earth-based ecosystem is extraordinarily difficult. Doing it inside a space habitat, where the closed system must also contend with artificial gravity gradients, radiation exposure to biological organisms, altered atmospheric pressure, and the absence of natural weather patterns, compounds the difficulty immensely. Smaller experiments have shown more success, but at much reduced scale. The Soviet Bios 3 facility in Krasnoyarsk, Siberia, operated sealed chambers in the 1970s and 80s, using wheat crops and chlorella algae to recycle air and produce food for small crews over periods up to 180 days. The system achieved roughly 80% food self-sufficiency and demonstrated effective carbon dioxide and oxygen cycling within its tightly controlled chambers. But Bios 3 housed only 2 to 3 people in a volume far smaller than any proposed habitat. Scaling its approach to 10,000 people is not a matter of multiplication. It is a matter of managing complexity that grows non-linearly with population and volume. The European Space Agency's Melissa program, a closed-loop life support research initiative launched in 1989, has spent more than 3 decades developing a bioregenerative life support system based on interconnected compartments, photosynthetic bacteria and algae for carbon dioxide removal and oxygen production, higher plants for food and additional air processing, and microbial bioreactors for waste decomposition and nutrient recovery. The program has produced substantial scientific results and validated individual subsystems, but a fully integrated, human-occupied, closed-loop demonstration at meaningful scale has not yet been achieved. The individual compartments work, connecting them into a stable, self-regulating whole that operates continuously for years without intervention remains an unsolved problem. The International Space Station's life support system demonstrates both the remarkable achievements and the hard limitations of current recycling technology. The station's water recovery system reclaims approximately 98% of all water aboard, including processed urine, cabin humidity condensate, and water recovered from carbon dioxide processing through the Sabatier reaction. This is a genuine engineering triumph. The system processes what most people would consider utterly undrinkable waste streams and produces water that meets or exceeds the purity standards of most municipal water supplies on Earth. Astronauts drink recycled urine and sweat without hesitation because the chemistry works. The oxygen generation system electrolyzes purified water to produce breathable oxygen, splitting water molecules into hydrogen and oxygen gas. A Sabatier reactor takes the hydrogen and combines it with carbon dioxide exhaled by the crew, producing methane and water. The methane is vented overboard, lost permanently, and the water is fed back into the electrolysis system. This loop recovers some of the oxygen locked in carbon dioxide, but not all of it. The current system recovers only about 42% of the oxygen from crew-exhaled carbon dioxide. NASA is working toward a goal of 75% recovery for deep space missions, using alternative chemical processes that convert carbon dioxide and hydrogen into solid carbon and water rather than methane and water. But even 75% is not 100%. The remaining 25% of the oxygen must come from somewhere, either from stored reserves or from water electrolysis fed by new water. Food is supplied entirely from Earth, roughly 1.7 kilograms per person per day, launched on cargo vehicles at enormous cost per kilogram. Solid waste is collected, sealed in containers, and either returned to Earth or incinerated in the atmosphere aboard departing cargo vehicles. The station depends on regular resupply missions for food, for water to replace the 2% not recovered, for replacement filters and catalytic beds and pump components, and for the spare parts needed to keep the life support hardware functioning. Cut the resupply line, and the station becomes uninhabitable within months. It is a brilliantly engineered life support system. It is not a closed one. For a city-sized habitat thousands or millions of kilometers from Earth, there is no resupply line. Every percentage point of unrecovered water, every fraction of lost oxygen, every gram of nitrogen that escapes the cycle must be made up from internal reserves or external mining operations. And even small losses compound relentlessly over time. Consider the arithmetic of imperfect recycling. If a habitat recovers 99.9% of its water each day, an extraordinarily high recovery rate, better than anything demonstrated in space, it still loses 0.1% daily. Over the course of a year, that daily loss compounds. After 365 days at 99.9% daily recovery, the habitat retains only about 69% of its original water supply. Nearly a third of the water is gone. After 3 years, less than 40% remains. After 10 years, the reserves are functionally depleted. A system that sounds almost perfect, 99.9%, is actually catastrophically leaky when measured over the timescales. A permanent habitat must endure. To sustain a habitat for decades, water recovery must approach 99.99% or higher. That final fraction of a percent, the difference between 99.9 and 99.99, is where the engineering becomes almost impossibly demanding. Every seal in every pipe must be virtually leak-free. Every evaporative loss must be captured. Every chemical reaction that binds water into a non-recoverable compound must be prevented or reversed. The tolerance for imperfection shrinks to nearly zero, and it must stay there for the entire operational lifetime of the habitat. Water is actually the easiest cycle to close. Nitrogen is harder, phosphorus is harder still. These elements are essential for biological life, but do not exist in gaseous form under normal conditions, which means they cannot be scrubbed from the atmosphere the way carbon dioxide can. They must be recovered from solid and liquid waste through decomposition, composting, and chemical processing, slower, messier, and less efficient processes than gas phase recycling. If phosphorus leaks out of the agricultural cycle bound into insoluble mineral compounds in the soil, or lost into wastewater sludge that cannot be fully reprocessed, the habitat's ability to grow food degrades year by year. There is no atmospheric reserve of phosphorus to draw on. Once it is lost from the cycle, it is gone unless the habitat can mine replacement material from an external source. This is why a city-sized habitat cannot simply be sealed and forgotten. It requires active, continuous, expert management of its ecological systems. Soil chemistry must be monitored and corrected. Microbial populations must be maintained in balance, the right bacteria for nitrogen fixation, the right fungi for phosphorus uptake, the right decomposers for waste processing. Crop rotations must be planned to prevent nutrient depletion. Pest species must be controlled without disrupting beneficial organisms. The interior atmosphere must be continuously analysed and adjusted. A single undetected imbalance, a surge in soil acidity, a crash in pollinator populations, an algal bloom in the water recycling system can cascade through interconnected biological networks with consequences that are difficult to predict and harder to reverse. And while the ecologists struggle with biology, the mechanical engineers face their own war of attrition. Every machine in the habitat has a lifespan. Pumps wear out, seals degrade, bearings corrode in the humid, oxygen-rich atmosphere that humans require, but that accelerates oxidation of every exposed metal surface. Filters clog with particulates from agricultural dust, human skin cells, fabric fibers, and the fine debris of daily life in an enclosed space. Wiring insulation becomes brittle under years of thermal cycling and low-level radiation exposure. Sensors drift out of calibration so gradually that the error is undetectable until a system operates outside safe parameters. Valves stick from mineral deposits left by recycled water that is never quite as pure as the specifications demand. Heat exchanger surfaces foul with biofilms, thin layers of bacteria that colonize any wet surface and reduce thermal transfer efficiency by insulating the metal from the fluid. Circuit boards develop solder joint fatigue from years of thermal expansion and contraction. Structural fasteners loosen under vibration from rotating machinery. Pipe joints develop stress fractures from the relentless centripetal loading of spin gravity. None of these failures is dramatic. None of them triggers an alarm on the first day. They are slow, silent, incremental. A pump that ran at 98% efficiency for 5 years now runs at 91%. A filter that lasted 8 months before needing replacement now lasts 6. A seal that held for a decade develops a seep so small it takes weeks to detect. Each individual degradation is manageable, but they accumulate, and in a habitat with tens of thousands of mechanical components, degradation is always happening somewhere. The question is never whether something is failing. The question is whether the habitat can repair failures faster than new ones appear. On Earth, when a water pump breaks, you drive to a hardware store and buy a replacement. On the International Space Station, you wait for the next cargo mission from Earth. On a city-sized habitat far from any supply chain, you manufacture the replacement yourself, or you do not get one. This means the habitat must contain not just life support systems, but the industrial capacity to rebuild those systems. A machine shop capable of fabricating replacement pump housings, valve bodies, pipe fittings, and structural fasteners from raw metal stock. An electronics workshop capable of producing circuit boards, sensors, and control systems. A chemical processing facility capable of synthesizing lubricants, sealants, adhesives, and catalytic materials. A glassworking shop for replacement window panels and optical components. A textile facility for replacement gaskets, filter media, and insulation material. Each of these facilities requires its own equipment, its own raw material supply, its own skilled operators, and its own maintenance cycle. The factories that keep the habitat alive must themselves be kept alive by smaller factories, which must be kept alive by workshops, which must be supplied with tools that also eventually wear out. This is the maintenance recursion, and it has no bottom. Every system that supports human life depends on other systems that also require maintenance, which depends on still other systems, in a chain that extends downward through layers of industrial complexity until it reaches the raw material supply and the energy source. If any link in that chain breaks and cannot be repaired from internal resources, the habitat begins a slow decline, not an immediate catastrophe. Maintenance failures rarely kill quickly, they kill gradually. A pump that cannot be replaced is bypassed. The bypass reduces system capacity. Reduced capacity means tighter margins. Tighter margins mean the next failure has worse consequences. Over months and years, unkept maintenance accumulates like debt, compounding silently until the system can no longer sustain the population it was built for. The International Space Station's experience illustrates this reality at small scale. Station crew members spend a substantial fraction of their working hours on maintenance, replacing filters, servicing water processing equipment, repairing air circulation fans, troubleshooting electrical anomalies. This is on a station that receives regular resupply of spare parts from Earth. A city-sized habitat must perform all of this maintenance using only what it can produce internally, at a scale hundreds of times larger, for a duration measured in decades rather than years. The maintenance burden does not scale linearly with size. It scales with the number of components, the complexity of their interactions, and the consequences of their failure. The habitat needs more than engineers. It needs a civilization, not a crew, not a staff, a complete, functioning human society with the full range of skills, institutions, knowledge systems, and social structures required to operate and maintain an artificial world indefinitely. Farmers to tend the crops, engineers to maintain the machinery, doctors to treat the population, teachers to train the next generation of farmers, engineers, and doctors, administrators to coordinate resource allocation, scientists to monitor the ecological balance and develop solutions to problems that have not yet occurred, technicians to operate the manufacturing facilities, skilled tradespeople to fabricate replacement parts, programmers to maintain the automation systems, and people to do the 1,000 other jobs that any functioning community requires: cooks, counsellors, sanitation workers, emergency responders, archivists, mediators. But the list of occupations only describes the labour. It does not describe the social machinery needed to coordinate that labour under conditions no human community has ever endured. 10,000 people sealed inside a pressurized container for their entire lives must develop systems of governance that can allocate scarce resources fairly, resolve disputes without the option of separation, manage population size within the carrying capacity of the agricultural and life support systems, and enforce maintenance obligations that are literally matters of life and death. On Earth, people who disagree with their government can emigrate. Communities that mismanage their resources can import what they need from elsewhere. A city whose water supply fails can truck in bottled water from a neighbouring state. Inside the habitat, none of these release valves exist. There is nowhere else to go. There is no neighbouring state. There is no outside supplier. Every decision about resource allocation, how much water goes to agriculture versus personal use, how many hours each person must contribute to maintenance work, who receives medical priority when supplies run low, becomes a question with existential weight, because the wrong answer can begin a chain of consequences that degrades the habitat's ability to support life. Population management introduces what may be the most difficult governance question of all. The habitat has a carrying capacity. Its agricultural systems can feed a specific number of people. Its life support can process air and water for a specific population. Exceed that capacity, and the system degrades for everyone. This means the community must collectively regulate its own reproduction, a decision so deeply personal and politically sensitive that no human society has ever sustained such regulation voluntarily over long periods without coercion or crisis. Yet inside the habitat, unchecked population growth is not a policy debate. It is a death sentence delivered in slow motion through declining food rations and overtaxed air recycling. The psychological dimension is equally relentless. Every resident of the habitat lives with the permanent knowledge that a thin wall of engineered material separates them from instant death. There is no horizon to walk toward. There is no open sky, only a curved ceiling that reminds you with every upward glance that you are inside a machine. The psychological literature on isolated and confined environments, submarines, Antarctic research stations, long-duration spaceflight simulations consistently documents elevated rates of depression, interpersonal conflict, sleep disruption, and a phenomenon researchers sometimes call the third quarter effect, where morale drops sharply when the confined group realizes it is past the midpoint but still far from the end. Inside a permanent habitat, there is no end. The confinement is the life. Designing social systems, mental health support, and cultural institutions that sustain human well-being under permanent enclosure is an engineering challenge every bit as demanding as maintaining the air, recycling equipment, and far less well understood. If the habitat's population is too small, it cannot sustain the full range of specializations needed to maintain all its systems. If the population is too large, the life support and agricultural systems may not be able to feed everyone. The population must be sized to match the habitat's carrying capacity with sufficient margin for demographic fluctuation, while simultaneously providing the labor force diversity needed to keep every critical system operational. This is not only an engineering constraint, it is a sociological one, and it means the habitat is not just a building project. It is the deliberate creation of a community that must possess, collectively, all the knowledge and capability required to keep itself alive. Knowledge preservation becomes critical across generations. The first generation of habitat residents will include the engineers who designed and built the systems. They understand the machinery intimately. They know its quirks, its failure patterns, its undocumented workarounds. They know which valve sticks in cold weather and which pump needs its bearings replaced 6 months before the manual says. The second generation learns from them, but second-hand through instruction and apprenticeship rather than through the original experience of design and construction. The third generation learns from the second, at one further remove from the source. Over time, institutional knowledge degrades unless it is actively maintained through rigorous education, meticulous documentation, structured apprenticeship programs, and mandatory hands-on training. A habitat that loses the knowledge of how to repair its own water recycling system is functionally doomed, even if the physical system itself is still repairable by someone who understands it. The library must write its own books. The school must train its own teachers. The chain of expertise must never be allowed to break, because there is no university back on Earth to retrain a generation that has forgotten how the plumbing works. This is the weight that no science fiction movie shows you. Not the gleaming corridors or the panoramic windows, or the elegant artificial sky arcing overhead. The weight is in the sewage processing plant that must run every single day without fail, in the carbon dioxide scrubbers that must be rebuilt from locally manufactured parts every few years, in the agricultural soil that must be tested, amended, and managed with the precision of a chemistry laboratory, in the water pipes that corrode slowly in a humid, oxygen-rich atmosphere and must be inspected, repaired, and eventually replaced using metal refined from asteroid ore, in an onboard smelter operated by technicians who are trained by technicians who are trained by the original crew. The habitat is not a vehicle carrying passengers across a void. It is a life support machine the size of a small city, and every part of it, structural, biological, mechanical, chemical, social, must function continuously in concert, without resupply, without rescue, without the vast planetary systems that make earthbound life effortless by comparison. On Earth, if a city's water treatment plant fails, water can be trucked in from neighbouring towns. If crops fail in one region, food is shipped from another. If the air becomes polluted, wind disperses the contaminants across an entire atmosphere. If the soil is depleted, nutrients can be imported from mines thousands of miles away. These backup systems are invisible because they operate at planetary scale, distributed across continents and oceans, and an atmosphere so large that local failures are absorbed without consequence. Inside the habitat, there are no backup continents. There are no neighbouring towns. There is no wind to carry away pollution, no ocean to buffer temperature extremes, no geological cycle to replenish minerals. Everything that Earth does passively, automatically, and at no cost, the habitat must do deliberately, mechanically, and at enormous ongoing expenditure of energy, labour, and materials. The habitat is civilization stripped down to its barest mechanical requirements and forced to sustain itself inside a sealed container with no margin for error. Think about everything Earth does for you right now, in this moment, without being asked. Gravity holds you to the surface. The atmosphere presses against your skin at 101 kilopascals, keeping your blood from boiling, your lungs from collapsing, your body from exploding into vacuum. The magnetic field wrapping the planet deflects a continuous barrage of charged particles that would otherwise strip away the atmosphere and irradiate every living thing on the surface. The ozone layer filters ultraviolet radiation that would blind you and burn your skin within minutes of unprotected exposure. The water cycle cleans and redistributes trillions of tons of water every day without a single pump. The carbon cycle regulates atmospheric composition across billion-year timescales without a single sensor. The nitrogen cycle fertilizes every ecosystem on the planet without a single factory. The soil beneath your feet contains more microorganisms in a single handful than there are stars in the Milky Way, and every one of those organisms plays a role in decomposing waste, recycling nutrients, and maintaining the chemical balance that allows plants to grow. You do not maintain any of these systems. You do not monitor them. You do not even think about them. They simply work, because they have been working for billions of years, refined by an evolutionary process so slow and so vast that no human institution could replicate it. Inside the habitat, every one of those systems must be replaced by something that humans designed, humans built, humans monitor, and humans repair. Gravity is a motor. The atmosphere is a sealed tank with a chemistry lab attached. The magnetic shield is 10 million tons of rock. The water cycle is a network of pipes and filters and bioreactors. The soil is a manufactured substrate inoculated with carefully selected microorganisms that must be monitored for population balance every growing season. Nothing works by itself. Nothing runs on autopilot. Nothing has been tested for longer than a few years at the scales required. And this is what makes the question of building a spaceship bigger than a city so much harder than it first appears. The difficulty is not size. Humans have built structures larger than cities. Highways, aqueducts, power grids, these span continents. The difficulty is not even the hostile environment, though vacuum, radiation, and microgravity are brutally unforgiving. The difficulty is completeness. The habitat must be complete. It must contain, within its walls, every single function that a planet performs for the beings who live on it. Gravity, atmosphere, magnetic shielding, thermal regulation, water cycling, nutrient cycling, waste decomposition, food production, energy generation, material manufacturing, knowledge preservation, social organization, medical care, education, governance. Every one of these functions must work simultaneously, continuously, and indefinitely, and the failure of any single one can, over time, bring down all the others. No object in human history has ever been asked to do this. The International Space Station does not do it. Nuclear submarines do not do it. Antarctic research bases do not do it. All of them rely on Earth for critical inputs: food, fuel, spare parts, fresh personnel, emergency evacuation. A city-sized space habitat cannot rely on Earth. That is the entire point. It must carry everything. It must be everything. And the engineering required to make that possible is not the engineering of building something big. It is the engineering of building something whole. The terrifying part is not that the ship would be larger than a city. We know how to build large things. The terrifying part is that the ship would have to be more complete than any city has ever been, more complete than any nation, more complete than any closed system ever attempted by any civilization in the history of the species. It would need to carry not just people and provisions, but the entire operating system of human existence, compressed into engineered walls maintained by mortal hands, turning endlessly through a void that provides no air, no warmth, no water, no forgiveness, and no second chances. That is what it actually means to build a spaceship bigger than a city. Not a vessel, not a vehicle, a world. Manufactured, fragile, and kept alive only by the unbroken commitment of every generation that lives inside it to maintain, repair, and renew every system that stands between them and the absolute emptiness outside. The ship is not crossing an ocean. The ship is the ocean, the sky, the soil, and the atmosphere. It is everything. And building everything, in a universe that gives nothing back, may be the hardest thing our species will ever attempt.